Board. All right, what are your, give me one at a time there, shorthands.
3, C, and D. I know, like, I've done it and I have the work in my book, but I don't know like how to do it. Like if I got it on a test, I don't know like how to work through it myself. Do you know what I mean?
Yeah, I think I do. Okay, so the question says, in a physics experiment on static friction, two objects made of identical material are tied together with a string. First object has a mass of 5, the second has a mass of 3. Okay, so for all intents and purposes, it's one thing with a mass of 8 because they're tied together. And then I don't like how that's not super clear. That looks better. Okay, so it's a mass of 8. Students measure the maximum force of static friction as 31.4. So Fs max equals 31.4. Okay, so jumping down to C, it says a student pushes the 3 kilogram object with a force of 15 newtons down. What are the magnitudes of the maximum force of static friction and the tension now? Okay, so they've added 15, a force of 15, so it's 15 newtons. So this plus, and I know like it's talking about the 3 kilogram one, but it doesn't matter if they're tied together. So plus 15 newtons down. So what this means, so let's figure out what 8 kilograms is as newtons. So 8 times 9.8. Stop me anytime I'm going too fast here. 8 times 9.8. So I'm figuring out normal force. So that's 78.4 newtons, and that's down. So the total will be both of these, 78.4 plus 15. So that's 83. So it's 93.4. This is the normal force for this question.
Yeah, I got that far.
Okay. And so static friction. Okay, so for A, the coefficient of static friction, what was that, please? Oh, I'm getting a phone call. I'm just going to make this really quick. Hang on, sorry. I'll call you back. I'm in class. Sorry, yeah, what was the coefficient of static friction, please?
I don't know. I'm just looking back in my sheet.
Oh, okay.
Oh, it's 31.4, right?
No, that's Fs max. What's the coefficient of static friction?
Oh, I'm looking. I don't know. I have to redo it.
Okay, well here, I'll just look in the back. Hang on, that's fine. I just don't want to do it. Page 178. Number 3A is 0.4. 0.4. Okay, something caught my eye here. It says tied together. That's different from being connected with a string because I saw something, they pull on the first object, tension in the string. Okay, so they aren't like one complete solid necessarily. Student pushes. What are the magnitudes? No, it should still be the same. Static friction is 0.4. So mu s equals Fs max over Fn. Mu s is 0.4 equals Fs over, this is our new normal force. So it's 93.4 times 0.4 to get the static friction. 37.36. Am I running out of room here? It used to be 31.4, but now it's 37.36.
So how can we use Fs max before and then use like, I don't know, like there's like two different forces of friction that we're working with, right?
Yeah,
like the one that we're finding, and then there's the one that they give us.
The trick here, like they're telling you it's a 3 kilogram box or whatever and a 5 kilogram box, right?
Yeah.
What we need to do, because when someone's applying 15 newtons of pressure onto this thing going down, what we need to do is convert this into mass. If this were a mass, what would it be? And then you can add it on to this. So for example, so 15 newtons, F equals mg. So force of 15 equals m times 9.8. Divide both sides by 9.8. And essentially we've added 1.53 kilograms. Somebody pushes down with 15 newtons, it's the same as them adding 1.53 kilograms. Because if I told you it's 3 and 5, well, now it's 4.5 and 5. Well, that makes that makes it way easier, right?
Maybe.
You're
I don't know.
you're just converting that force to mass.
Okay.
Does that kind of make sense? Is there something I'm skipping over?
No, I'm just looking at the sheet.
Okay, yeah, no, look at it.
So for the coefficient of friction, that doesn't change when you add more mass?
Correct.
Okay.
Correct. That's a good question. So then, like if we say like mu s equals fs max over fn, if this fs max, that's the greatest, the maximum amount of static force being used to stop something from moving. So if we increase the mass of the object, all that does is that increases this. And if this increases, this has to increase because this is a static figure. That's like that table that we were given. It's like rubber on ice, rubber on rubber, rubber on dry concrete, rubber on wet concrete, steel on steel, all that other stuff. Because when two surfaces rub against each other, they have a coefficient of friction. So that doesn't change. So it's like if in your shoes, that was Nathan that I'm talking to?
Yeah.
Okay, so your shoes, they have a rubber sole. They're going to have some kind of coefficient of static friction. And if we're having a tug of war and I'm able to pull you like so that your feet kind of squeak and slide on the floor, there's a certain amount of force I'm going to have to do. Now, if your sister jumps on your back, I'm going to have to pull harder. This doesn't change, but the normal force has changed. There's more pressure between the two surfaces.
So the forces change, but the ratio between them would stay the same.
Exactly. Exactly. Did your sister tell you she saw me the other day? Nathan?
Yeah.
That's important to cover as well. Where are we at? Ada, I just about called you Abigail. Ada, thoughts, comments, questions?
I think, are you recording this?
Yeah.
I think I just need to go over it slowly by myself as well.
Okay.
And it's asking for the tension too.
If the student pushes the 3 kilogram object and the 3 kilogram object is the one that's getting force put on it, then nothing's going to change because there's no change in the 5 kilogram object. But if you're pulling the 5 kilogram object and dragging the 3 kilogram behind it, well, now there's going to be a change because that 3 one is functionally heavier. Does that make sense? Like here, let me draw it. So for example, if I pull the 3, let's say I'm going to pull them. I pull the 3 and it's attached to the 5. This tension is going to be whatever. I don't know. What's any idea what it is? I'm just going to say 12. So let's say there's a tension of 12 when I'm pulling the 3 and I'm dragging the 5. Now let's say I make this one 10 times heavier. If I pull this, nothing's changing over here. Nothing's changing over here. But if I pull this way and I'm pulling 30, that's going to be pretty heavy. If I get rid of a bunch and now I'm just pulling 3, it's going to be way lighter now. Depends which one's pulling, which one's dragging.
Okay.
Does that make sense?
Yep.
Well, aren't they dragging the second? Like they're pulling the 5 one, and the mass on the 3 would kind of change, I guess, with added
Yeah.
force.
Yeah, that looks like that's part D. Part C, it's asking if you're pulling this. Does the tension here change? No.
No, they're pushing down on the 3 kilogram one. They're still pulling from the 5.
Oh, okay, then it would change. Oh, but look, oh, sorry, I read it wrong. Yeah, you're right. I'm sorry. The tension would change if you're pulling on the 5. Yeah, you're right. The tension, well, it's kind of what I've been saying of just if you're pulling on one versus the other. So nothing I said is wrong. I just misread the question. Does that make sense?
Yeah.
Yeah.
It's just like you're pulling a sled, and your little friend, cousin, sister, brother, whatever pet is on that. And now if 2 other people jump on the sled, it's going to get harder. There's going to be more tension in that rope. But if a different person was pulling the same dog on a sled, the tension in the rope doesn't change.
So how do you calculate the tension again?
Acceleration. You figure out force and acceleration. Once you know how it's accelerating, you have to know how much force is being applied to it.
And which mass would you use?
You use both masses.
Okay.
Both masses because they're connected. You start with okay, so here, let's do this. If I am, where's the top of this? Okay, static first. Okay, what is coefficient of static? What is the magnitude of tension of the string? Okay, so it's 31.4 newtons to move them. So you've got the 3 and the 5, and it sounds like you're pulling it from here. And it's 31.4. That's what FS max means, and which is that kind of double-edged sword. So that's what it'll take. This is the maximum this can pull out, put out, and so that's what you're going to pull with. So now 31.4 equals mass times acceleration. This is 8. 31.4 equals 8a, and then you solve for that acceleration. Once you have that acceleration, you figure out how much force is needed for this to go at that acceleration. It's one of those kind of working forward then backward ones. It's similar to the pulleys. You use both masses, use the one mass to get it going, then both masses for the acceleration. Does that make sense?
Yeah.
This test is a little bit, I think, who knows, but I think it's a little bit shorter, so we can deal with some questions in the beginning of class too. Like if I'm not saying to put them off, I'm just saying if you have questions tomorrow, we can talk about some stuff.
So if it said if the force like changes from the 3 to the 5, for tension, it doesn't make a difference, right? Because they're pulling the 5 and the 3.
2 objects tied together. First is this. Students measure the maximum force. What is the coefficient? What is the magnitude of the tension of the string if they pull? Okay, so what's the first? The first is 5. Okay, so if you're pulling on 5 and you increase the weight of 3, the tension is going to go up. If you decrease the weight of 3, tension is going to go down. You don't have to pull as hard, provided you're always pulling from the 5.
So if the tension moves from the 3 to the 5, though,
Like
and by
the
the
force
same,
going down,
yeah.
then the tension wouldn't change here from what it was originally.
Oh, right.
Right, because it just weighs the same.
Oh.
That's like me saying, like if I'm pulling a sled and you've got a dog, I'm not an artist. You're pulling a dog. If it's me pulling this dog, or if it's Mr. Taves pulling this dog, if we're going the same, because he's that much bigger than me, if we're going at the same speed here, the tension in this rope is going to be the same. Now, if Mr. Taves hops on the dog and I'm pulling, the tension is going to increase because the normal force here is increasing. It's going to be more friction.
But we were calculating the tension in like the pulling string, that wouldn't make a difference whether the force was on the 5 or the 3, right?
Correct. On the pulling, well, yeah. If it's one or the other, yeah, this will be the same.
Okay.
Yeah. as long as it's one or the other. Yeah, because it's total mass. Yeah.
So the maximum force of static friction wouldn't change, but the tension would.
Well, the maximum force of static friction would change if you put pressure on either one of these. Yeah, it would go up.
But if it was on the 3 or the 5,
Either one. Static friction is going to be more. Remember, where's this other page? Like if I mu s, this is the part that doesn't change, and this was 0.4. So if one of these increases, the other one's going to increase.
so it doesn't matter which one it's on, it'll change either way.
Yeah. And like the friction depends on normal force. Like you can't kind of objectively change this unless you change this. If I put more weight on or put more mass on, or I lift one end, or like I take some weight off or whatever, that'll cause the fluctuations. This just kind of does what it does. Does that make sense?
Yeah.
Nathan?
Yeah.
Kate? How many people are even here? Yeah, it's just us 4 girls. Next question. Am I going too fast? Are we ready for next question?
Yep.
Okay, who wants it?
I have another one on the same page.
Let's do it.
Number 5.
Okay.
I got up to D, then I didn't know how to get that.
Okay, when the final washer is placed in the bucket. Okay. So mu k equals, okay, so first of all, this is 5D, page 179. 5D, page 179. Mu k equals 0.34. The mass of that bucket, full bucket, is 120 grams plus, what is it, like 34 or something? How many washers?
I had 86 washers.
Okay, 86, I just couldn't remember. 86 times, what are they each, 0.02 or something? Yeah.
Yeah.
20 grams. Okay, so times 20. This is all going to be in grams. So that's 86 times 20 equals that, plus 120 equals that, divided by 1,000. So it's 1.84 kilograms. This is going to provide the force to move this thing. So we've got this, I'll draw it. So this is 4.4. It goes around. Well, that's perfect. Bucket. Oh crap, it all just went to crap. I don't know what this is. Anyways, it's 1.84. I was doing so good, I can't even draw a bucket. I was happy with that I drew a block. Okay, so anyways, this F equals mg. This is going to be the force on the system. This is, if there's no bucket here, it's just you pulling on this string to get this thing moving. So the force is dictated by the mass. The mass is 1.84. Gravity is 9.8. So 18.032, 18.032 newtons down. That's the force on the system. Are we okay so far?
Yes, I did this stuff.
Good. So now F equals MA. We have 18.032, 18.032 equals the mass. Now it's of both. 4 point, so that's 5.24, 6.24. So 6.24 times A. Divide both sides by 6. Oh, come on. I can't even do numbers. 6.24, ka-ching. Acceleration, 18.032 divided by 6.24, 2.9 if we're doing 2 sig figs, 2.9 meters per second squared. What is it asking? Of the block. I'm talking about the block, so that's going to go to the right. Block is going to block's going to go to the right at 2.9 meters per second squared. Mass of the bucket is the force on the system, but they're connected with this taut string, rope, wire, whatever. So you treat them as one unit as far as their acceleration goes. Thoughts, comments, questions?
I'm just looking at it. The F, I have written on my sheet that the 18 is FS max. But is that just regular force?
That this force is the oh, it's 1.84, not 18. Oh no, sorry, I'm looking at this wrong. Okay, sorry, what was the question?
I don't know. I'm just confused what the F is because on my sheet I have it as FS max, but it's not, right?
It's totally not. Like, this isn't even a static friction question.
Yeah, okay.
Yeah, this is kinetic.
That was throwing me off.
Yeah,
Okay.
yeah. Oh, hang on one second. Hang on one second. Hang on one second. Hang on one second. Like the mu k is 0.34. I did this question as if there was no friction. Is that what you were about to say, Nathan?
No,
Oh,
it was
okay.
different.
Well, it is important to figure out, like, we have kinetic friction working against this, and I didn't put that in here, and I apologize. Mu k equals Fk over Fn. 0.34 is the coefficient of kinetic friction for this block. So this force of 18 newtons is going to be lessened by the force of friction. Sorry, I got carried away here. So mu k 0.34 equals Fk over 4.4 times 9.8. So Fk is equal to 0.34 times 4.4 times 9.8, 14.6608, 14.6608. So this essentially is negative force. This is positive force. So what I did here, I jumped the gun. I shouldn't have done this yet because it's 18.032 minus this. So our net force, 18.032 minus 14.6608. Ah, 18.032 minus 14.6608 is 8. Oh, do I not know how to work a calculator? 18.032 minus 14.6608. Better. 3.37. So that should be the acceleration is actually like around 0.5. Sorry.
Oh.
Is that better?
Yeah.
Sorry
Okay.
about that. So it's like 3.37 equals 6.24 A. Three 3.37 divided by 6.24. Yeah, 0.54.
Will there be questions like this on the test?
You know, I was close to doing when you asked this question to say, you know what, there's no pulley questions on the test, but still the dynamics of force and friction and stuff, like there is that, but there are no pulley questions. Does that kind of answer your question? You will still need to know how, you know, like friction kind of competes with the applied force and stuff like that, and normal force and how that stuff, you know, factors in, but there are no pulley questions. You don't have to figure out how many washers you need to put in a bucket to cause a block to move. No.
Okay, good.
Sorry All right, what were we gonna say before, Nathan, before I realized my mistake?
Can the coefficient of friction, like, it would only be realistic up to 1.0,
Yeah,
right?
Yeah.
So like if it's 5.4, then that would never happen.
right.
Okay.
There's something off there. Other questions? From anyone?
I have more questions if nobody else has them.
Did you have any questions, Kate?
Well, I had a question just like sort of about the test in general.
Yep, go for it.
Well, I was wondering if I could like show my understanding in a different way, because
Instead of writing a test?
yeah,
Okay,
because I've sort of had, well, especially because for this unit, like we're writing sentences about like the athletic part stuff,
yeah.
and like I was just wondering if I could do something different for that part even, because I don't know how. Like I understand it, but I don't know how to show that on a test.
Tell you what, why don't we continue this conversation when I'm done with the other two? Is that cool?
Yeah.
Nathan, did you have any questions?
No, I'm just seeing if anything pops
Okay.
up.
Yep, no, that's cool. All right, Ada, it's your floor, sister.
Okay. I have some questions written down that are pretty obvious, so I'm just going through them to make sure.
Okay.
Um, okay, on page 199,
Yep.
question 23, it says to compare the magnitudes of the gravitational field strength and the gravitational acceleration at Earth's surface. What would you write for that? Like they're equal to 9.8 or they're
Yeah. Like you're not gonna get that kind of question on the test, but yeah, they're 9.8. It's 9.8 newtons per kilogram. Is the field strength, and the acceleration is 9.8 meters per second squared.
but one varies and one doesn't, right?
It depends how they vary in the sense of how close you are to the Earth's surface.
Oh, but I guess they both do.
Yep.
Because I was just thinking that the gravitational field strength is like an average, but I guess it depends on where it is. But
Yep.
so does the other one. So
Yeah, they're totally linked.
so
It's
they both vary with each other. So that would be another
different
thing.
on Mount Everest than it is like in Death Valley or whatever. Yeah.
Okay. Number 24. 2 ways to measure gravitational field strength.
Well, with a you could measure it with acceleration or with force, like with a scale.
I don't get that.
You know what? Because the day before a test, you don't need to. Don't worry about it.
Okay.
It's going to take you kind of further off of something and like that's not on the test at all, then I don't want you to take time with it right now.
Okay. I don't understand the graph, page 199, number 21.
Don't worry about it. You asked me this already, didn't you?
Yeah, I know, but I'm just like it's annoying me that I don't get it.
Don't worry about it.
Okay.
Don't worry about it.
I was like looking up videos and yeah. Um
Honestly, I have almost always had a skydiver question, but it's just the breadth of answers is too much for my brain. And then there's all these gray areas and there's all these what ifs. It's like, it's too much.
What type of questions will there be on the test regarding like the physics and cars and that sort of stuff, and the running shoes and the yeah.
So with cars, like you could be asked about tires, you know, different innovations that have been made to tires and seat belts and like crumple zones in cars and what are they called? Airbags. Just innovations, like what helps either to be safe or, you know, with sporting things to do more, to go further, faster, harder, whatever.
So it's kind of like the what and why short answer questions.
Yeah.
Okay. I think that's it. I'm still looking through, like I'm on page 201 of the practice. So I still have like a page left. So I might have a question tomorrow morning.
No worries. Or if it's, you know, during the school day, you can email and I'll most likely get back to you.
Okay.
Okadoke. All right, I'm gonna, no, I'm not hitting end. I'm just gonna stop recording.